So this time around, we're going to look at the intersection of two planes in space. So what do we need here? What do we need to understand? So here we're going to look at two planes and want to see how planes can intersect in space. So I can say that one plane is something like this. Okay, not coming out the way we want it to come out. So one plane is something like this. We can look at another plane. Maybe something like this. It can be anything really. So I want to see how we discuss how these planes can possibly intersect. So what do we see here? So usually there are three possibilities that you want to talk about when it comes to how planes intersect. And mostly here, their normals will play a very key role. We know to say when describing a plane, there's always going to be that part where you must specify exactly, give a vector that will be normal to the plane. For this one, we can say that maybe a normal that is going to be something like this. Now we're saying that by observing how the normals of the two planes are presented, or the expressions, how they look, we can conclude whether the two planes are parallel, or if they intersect. So just by looking at the normal, that might be enough. But otherwise, when it comes to the intersection of planes, there are three possibilities that we want to talk about here. Possibility number one is that the two planes are actually different planes, and they actually intersect in a normal way. And in this case, when we look at this possibility, here's what we'd expect to see. If these are the two planes and then we say that they intersect, then in this case, what we'll probably observe is that the space, or the point where the two planes intersect. So I'm trying to draw this so that it kind of makes sense. But of course, this is going to be, it's easier said than done. Okay, so let me make one of these slightly more. Yeah, this is going to be easier said than done. Okay, so say we had something like this. So in this case, we can say that if these intersect somewhere like along that point there. So what we see is that in this case, the point where the two planes intersect is going to be represented in form of a line. So it's not just one point where the planes intersect, but it's going to be an infinite number of points, and all these points will lie on that red line. So in this case, you have two distinct planes, and those planes intersect, and then it will then imply that their point of intersection is actually going to be described by a line. So that is what we get there. So of course the blue plane is going to be this one here. So I hope it kind of comes out to say that these two planes are intersecting. I hope it shows. And then we have one more plane, the vertical one. Perhaps I can present it with that color there. So of course that gets to go through the second plane there. So I only cut it through that red line there. Okay, then it gets to pop out right at the end here. Okay, so something like this. So in this case, we are saying that the point of intersection shows up as just a line that is right through that section. So if you have two planes that are distinct and then they intersect, we are seeing that here the solution set is a set of points that lie on a line of intersection. So all the points will lie on that red line there. This is condition or case number one. Here, of course, what we see is that we're going to have the normal to the blue colored plane going like that. We can say that is normal one. And then we have the normal to the white colored plane. We can draw it anywhere really. Say something like this, and we can say that is normal two, normal two. Okay, The two normals can also be presented right at the point of intersection. Right along that line, you can say one normal goes that way, and then the other one, which is vertical, can be drawn like that. It doesn't necessarily mean that the two must be perpendicular to each other. Of course, that possibility exists, but depending on how the two planes intersect, they might, most of the times, they won't even be perpendicular to each other. Okay, so case number 2, in terms of how they might intersect, it's possible that the two planes intersect, but if they are parallel to each other and they actually intersect, it can be that the two planes lie right on top of each other. So it can be that maybe this is one plane, and then you have a second plane that is parallel to the first one, but it lies right on top of the first one. So let's take this to be plane number 1. And then you have the second plane on top. Let's say the second plane is here. Okay, so if the two planes actually coincide with one another, then in such a case, you'll notice that all the points will also coincide. So a point on plane 1 will also be a point on plane 2 automatically. So in such a case, here, if the planes are coincident, then every point on the plane is a solution, because it will also be found on the other plane as well. Of course, it is a solution because here we're trying to find the points which belong to uh, the points at which the planes intersect. And since here the planes coincide, it will imply that they intersect at all points on either plane. So that is possibility number 2. Now, for the third part, we're saying that now it's possible that the two planes are parallel to each other. So here, of course, we're saying they coincide, but it's also possible that the planes are parallel and they do not coincide. So just like we saw in the first case, it can be that maybe you have one plane like this, and then you have maybe, okay, not completing. Okay, so you have one plane here, and then maybe another plane somewhere down here. But the two planes are parallel to each other. They don't, of course, and these can be very big planes, but basically here the two planes are parallel to each other. So still, in such a case, they will not have some point of intersection. So with the 3 possibilities described, now we want to see how we handle each one of these cases, and we're going to move on to look at some examples. So again, like always, we'll start with a few basic examples. After that, we'll go on to look at some questions from the tutorial sheet. Okay, so for our first example, we want to discuss the intersection of these two planes. So how do we do it? So, well, first thing that we want to do here is to extract the normal from these planes. So let's get the normal from plane 1. So from plane 1, we know to say that the normal will come from the coefficients of the variables. Here we have 2, here we have -1, here we have +1. So from plane 1, we're going to have 2i, then that's -1j, then plus 1k. So this is going to be plane 1, the normal from plane 1. When it comes to the normal from plane 2, again, it will come from the coefficients of the variables. So here we see that from x we have a 1, from y we have a 1 as well, and from z we also have a 1. So this will just be this. So these are the two normals for the two lines, and for the two planes, I mean. So when we compare these two normals, are the two planes parallel? Well, if the two planes are parallel, what do we expect? If this plane is parallel to another plane, so their normals will actually tell us all that. because if they are parallel, then it should imply that their normal must be related. So if the two planes are parallel to each other, it should follow that even their normals must be parallel to each other. So it might be that the normals are going opposite direction, but all in all, they must be parallel. If they're going in opposite direction, it will mean that if the one is ijk, it should mean that the other one should be negative I, negative j, negative k. So that is if they're like that. But of course, they might be going in the same direction and so on. But all in all, if the two planes are parallel, their normals must be the same. In this case, when you compare the two normals, they're different, telling us that the two planes are not parallel. So I can see that plane 1 and plane 2 are not parallel. So because they're not parallel, next thing that we want to see is, then do they intersect? So to check whether they intersect, what we're going to do is just get these equations. So get the equations of the two planes, and what we want to see is there some value of x, y, and z which ensure that they intersect, where such that for that value of x, it will satisfy the equation on top and the equation down, and it's the same thing for the value of y. So let's see, is such values possible? So to understand that, we'll just try to combine the two equations. So I can get these two expressions, we can just try to subtract. We notice that when you try to subtract this, of course, z is going to subtract out. So let's try to see if we can do that. When we subtract this expression, as I said, z is going to come out. What we're going to have is going to be 2x minus x, which will reduce as just x here. Then minus y will give us minus 2y. And then now we'll have negative 1 plus 6, because it will be negative 1 minus 6, so negative 1 plus 6, which will be plus 5. And on the right side, this is just equals to 0. From this expression, we now see that we can come up with an expression for y, for x I mean. So we end up with x is equals to 2y goes to the right becomes positive, 5 goes to the right becomes negative. We end up with this expression as the expression for x. We can hold on to this. Now, the next thing that we want here, we can define a parameter. And this parameter, we're going to define it in terms of one of the variables here. So it's up to you what the parameter is going to be really. But here, we can simplify it and then just let y be equals to a parameter t. What this implies is that for this equation that we selected, we can just put t where there is y, and this becomes x is equals to 2t minus 5. And notice that this reduces to a parametric equation for x for the line we're going for. Remember, if these two planes actually do intersect, then their intersection is a line. And a line can be represented either in parametric, symmetric, or vector form. So here, by defining y to be equivalent to a parameter t, we come up with an expression for x. And from here, notice that we can easily find everything else. Remember, the first expression will already be y is equals to this. This can be considered as the first parametric equation. Now we have x to be equals to that by substituting t where there is y there. So all we need now is to find what z is. And to get what z is, what do? I will just now go back to the original expression. So I can come back to the original expression here. We can just pick one of these expressions. I erase everything. You just pick one of them. Can get the first one. And for that first expression, where there's x, we'll put 2t minus 5. Where there's y, we'll put t. So that we come up with a parametric equation for z. If I make Z the subject, we'll have this 1 becomes positive, Y becomes positive, and 2x becomes negative. Now when we substitute, 1 will remain. Y, remember y is equals to t. Then we'll have 2, where there's x, we'll put 2t minus 5. So that now we have 1 plus t minus 4t plus 10. And when we simplify this and this, minus 3t, 1 and 10 gives us 11. So we have positive 11 minus 3t. So this becomes the parametric equation for z. So the line of intersection has reduced to parametric form with x equal to, we had that was 2t minus 5, and then y just equal to t, and then z being equal to 11 minus 3t. So this becomes the parametric equation for the line of intersection. So again, notice that the choice of what y is to be this, it's not set to say that this is what you must do. It just becomes a preference. Like, for example, when combining these two expressions, we might have decided to eliminate y instead of eliminating z. That would have also been possible, because here, if we wanted to eliminate y instead, would have just added here. Adding would have ensured that the first one that you eliminate would have been y instead. And had you done that, if you had added here, let me just show you how it would have continued just here. 2x plus x, that would have just been 3x. Y would have reduced to 0. Z plus z would have given you 2z. And then y, negative 1 minus 6, that would have been minus 7, is equals to this. Now you'd have just had to make one of these expressions subject to the formula. And if I would have gone for x, this would have been 7 positive minus 2z. And then divide both sides by 3. This would have been 7 over 3 minus 2 over 3z. Then from here, we would have just said, let z be equals to the parameter t. So that now, z, where there's z, this is where we'll put t. So the first parametric expression for x would have been in this form this time. And then a t here. So this is how it would have proceeded had we decided to eliminate y instead of z. So many different ways we could have continued with this expression, but the one we selected, these are the parametric equations that we ended up with. So our conclusion is the two planes P1 and P2 intersect, and their point of intersection is a line with parametric equations given as this. You could have given your solution in form of parametric equations or symmetric or vector form, completely up to you. See the trick here. Step one, compare the values of the normal. If the expressions for the normal are different, then the planes are not parallel. The planes are unique, they are distinct. If the planes are different, they are unique, it implies that they intersect. The question is, where do they intersect? In that case, you then go on to either, basically to eliminate one of the variables so that you remain with only, you do this either by adding or subtracting. But if they don't add to eliminate or subtract to eliminate one of the variables, you can still try to use multiply by a common factor, multiply one expression by a common factor, and then proceed to eliminate. That would also work. Okay, so I hope you guys got that. Let's look at another basic example. Example 2. Or basically, this is A, B, and E for the same expression. We're discussing the intersection of planes. And here, you can say plane 1 Let's look at our second example. In this case again, we want to discuss the intersection of these two planes. So first thing we want to do is let's check their normal. In the first plane, normal 1, again we're just getting the coefficients of the variables. So we have 2i minus j plus k here. Normal 2, we have 3i minus 9j. Then you have plus 6k. When you compare the two normals, they are different. So in this case, because the two are different, we see that these two planes are not parallel to each other. Instead, they will intersect. But where do they intersect? So to find their intersection, we'll get these expressions for the planes, and just like we did in the previous one, we'll try to find the point where they intersect. Remember, there are two possibilities if they intersect. Either they intersect everywhere, or they intersect just along a line. So completely up to us how we're going to proceed with this. But we see that here, if we subtract, nothing cancels. If we add, nothing eliminates. So because of that, we first want to scale these expressions up. So to scale these expressions up, I want to eliminate x. Let's go for x. So if we want to eliminate x by either adding or subtracting, we first have to, let's go by adding. We need to multiply this by 3 and multiply this by 2 so that they will have the same coefficient. So I'll multiply the first equation there by 3. I'll multiply the bottom one by 2. If I do that, then I'm going to subtract. If I multiply by negative 2, then it will mean that I'll just add to eliminate. But here, let me go with positive 2. So if I scale these up in this manner, what do they become? The equation on top, when I multiply by 3, it becomes 6x, then 3y, then 3z minus 3 is equals to 0. Scaling the one down by multiplying by 2, this will now be 6x, 9 by 2, that will be 18y, then plus 12z, then minus, that will be 4 now, is equals to 0. Now we see that we can subtract to eliminate. When we subtract this time, x would disappear. But what are we going to have everywhere else? So when we add for y here, we see that we're going to have minus 3y minus 18. So this becomes plus 18. Plus 18y. In the same way, when we add for z, we're basically subtracting there. So this is going to be plus 3z minus 4z. And then the other side, we have minus 3 plus 4. So this is now what we have here. So when we subtract this side, we're going to get 15y. And then when we subtract this side, we're going to get minus 9z. And then this side, when we subtract, we're going to get plus 1 is equals to 0. So this is what we are simplifying to. So here now, we see that this can divide through by 3. We can divide this equation by 3. 3 into 15 will leave 5. 3 into 9 will leave 3. Yeah, of course, then this will have to be a fraction. This will have to be 1 over 3. Yeah, so perhaps we can leave it like this. I don't want to have 1 over 3 there. Okay, so I can make one of these subject the formula. So I can make y the subject. So I can go with 15y being equals to 9z minus 1. So that now y is equals to 9 over 15z minus 1 over 15. So this is y is equals to 1 over 5, not 1 over 5, 3 over 5. 3 will go 3 times there, then 3 will go 5 times here. And then minus 1 over 15. So in this case, we can then now let z be equal to t. If we let z to be equals to t, then we'll have y is equals to 3 over 5t minus 1 over 15. And then using the expression for y and for z, we can then get one of these expressions. And then now we're trying to just get what x is going to be. So this is going to be 2x minus, where there's y, we're putting 3 over 5t minus 1 over 15. Remember, this has to be in brackets because y has a negative there. Then plus z, where the z, we're just putting t. Then minus 1 is equals to 0. So here we're just trying to make x the subject to the formula, so we'll keep it on the left. Everything else goes on the right. 1 will be positive, t will be negative. This whole thing will now be plus. The negative here will become positive as it goes to the right, to be 3 over 5t minus 1 over 15. Then of course now it's just a matter of grouping the like terms and simplifying. Of course you have to divide by 2 later on. So let's do that. So in the end, x would come out to be this. So that now our parametric equation for the line of intersection would be x is equals to 7 minus 1 over 5t. Next, y. What did we have for y? Let's check it out. For y, we had this. And then for z, we had z is equals to t. So these now become the parametric equations describing the line where the two planes intersect. Okay, consider this example now, where we have the two planes described like this. So in this case, what is happening? Where do these planes intersect, if they do intersect? So the first thing that we want to do is extract the normal of each plane. So from plane number 1, we see that the normal is going to be 1i. Then from y, we have 1j. And then from z, we have negative k. And then for the second plane, the normal would be 2i, and then 2j, and then minus 4k. Okay, so I'm trying to see if we did copy these correctly. So when you look at these look different. You see, what we want to look out for here is what would have made these slightly similar would have been if, let's say, this had a 2 here. Then you'd have seen that if you could factor out a 2 from this one, you would have seen it as 2 coming out from here. This would have been I plus j, then minus 2k. Notice that in this case, you'd have seen that normal 2 would have actually been equal to 2 multiplying normal 1. This would have been possible. But the way it is currently, we see that the two are different. So because they're different, we can conclude that here the two planes are not parallel because of course in the original problem that we're using, this 2 is not there. So this simplification is not possible. So since this is not possible, we then want to proceed with the second test, where we're trying to combine these two expressions to see what we end up getting. So in that case, similar to what we did in the previous method, of course, is there something that we can eliminate? Looks like we cannot eliminate anything. So we can scale up by 2. So here we're just going to multiply the top one by 2. The bottom one can be multiplied by 1. If we did that, this would be 2x on the top one, 2y minus 2z, then plus 4 is equals to 0. The bottom one would remain the same, 2x plus 2y minus 4z, then plus 8 here is equals to 0. Okay, now if we subtract, what do we see? When we subtract, we see that this will be 0, this will be 0, and this would survive. What are we going to get there? So this would end up giving us minus 2z plus 4z, and then this would end up giving us, let's see that, this is going to be 4 minus 8, which is going to be minus 4 is equals to 0. So now we have 2z minus 4 is equals to 0. And this is reducing to an exact value for z. Z is equal to 2. So z is reducing to just being 2 here. So in terms of simplifying this, it looks like, well, if we're not sure about how it is simplifying, maybe targeting to eliminate x or y, it looks like that is not working well for us. We can target to eliminate z, which is independent of x or y, because I know when I scale up z, when eliminating z, I won't have to worry about the other ones also disappearing. So I can target, so if I'm not comfortable with how this continues, I can target to eliminate z instead. If I wanted to eliminate z, I know I'd have to scale the top one by 4, so that if I scale the top one by 4, now I know z there will be the same, so that it will be easy for me to actually proceed from there. So I hope you've seen how I ended up concluding that, because I don't know how I would proceed there, because all the examples I see, at least I have 2 variables where I get to redefine one of the variables. Of course, you might conclude what the parameter might be there still, but if you're uncomfortable, it's easier to just choose a different one to eliminate. If I scale up the z parameter, this will now be 4x plus 4y minus 4z plus 8 here is equals to 0. The bottom one remains the same again. These are both minus, okay. And then we have 4 here is equals to 0. Now here we can subtract. We notice that now correctly, this will eliminate z for us. When we subtract here, we'll have 4x minus 2x, which will be 2x, 4y minus 2x, which will be 2y, and then z disappears. We have 8 minus 4, which is 4, is equals to 0. And now we have divide everything by 2, x plus y plus 4 is equals to 0. And then we can say x is equals to minus y minus 4. This is better, because here we can now say let y be equals to a parameter t. So now we have x is equals to minus t minus 4 as our first parametric expression. And then now, since we have y, we have x, we can get z. So I can pick one of our original expressions and then make the substitution. So I hope you guys have seen how I came around an uncomfortable situation. So here, where there is y, I'll put t. Where there's x, we'll put minus t minus 4. And then where there's z, we'll leave z. we see that t and t gives us 0. We now just remain with minus 4 plus 2 minus z is equals to 0. This is going to be minus 2 minus z is equals to 0. So now z is equal to minus 2. So this is what z has reduced to. So when it comes to presenting the parametric equations, we have x is equals to minus t minus 4. Then we have y is equals to just t. And then we have z is equals to minus 2. What this implies, these parametric equations where x is equals to x0 plus a t, and then y is equals to y0 plus bt, and then z, the parametric equation is supposed to be z0 plus ct. If z shows up without the t parameter, it just implies that this number here was a 0. That's why it multiplied with t to give us a 0 there. But generally, these are the parametric expressions for the line of intersection. I hope you guys have got that part. So in an event that these two planes maybe just slight difference, if we had a 2 there as the coefficient of z, what would have happened here is first observation would have been when getting the normals. For plane y, you'd have had I, you'd have had j, then you'd have had minus 2k. For plane 2, you'd have had 2i, 2j, and 4k. Now, in this case, you should have noticed, or you could have noticed that the two normals, even though they might not be identical straight out, they are kind of related. When you look at the way it is, if you factored out a 2 from normal 2, what you notice is that what will remain is I plus j minus 2k. And when you see this, you should observe that this is exactly the same as normal 1, meaning that normal 2 is actually related to, you'd get normal 2 if you just doubled normal 1. So these two normals are actually the same. Since the normals are the same, what does this imply? Notice that even if you tried to say, okay, let me find the point of intersection, if you got those two and said, let me find the point of intersection, and say, okay, let me try to add them, and then you notice that nothing simplifies directly, and then you say, okay, let me try to scale them up. For this scenario, when you try to scale them up, notice that you'd have to multiply the top one by it, regardless of the variable you try to eliminate. Whether you try to eliminate z, you have to multiply by 2 first. Try to eliminate y, you have to multiply by 2. Even if it's x, you'd have to multiply by 2. If you multiply it by 2, you'd have 2x, you'd have 2y, you'd have 4z. And then this would also be 4. The bottom one would still be the same. But in this case, what do we observe? If you subtract now, what would happen? Here, you'd get 0. Here, you'd get 0. Here, you'd also get 0. Even here, you'd end up with a 0. What are we seeing? You'd end up with 0 is equals to 0. What is this telling us? The two planes are the same. The two planes coincide. The two planes are basically overlapping. These two planes are coinciding. So this is the conclusion we could have made in an event that is what we had.